This is a problem-solving day, okay? There's a lot of stuff that I inevitably talk about in a course of this sort that is theory, that is big ideas about how energy is transferred, big ideas about how equilibrium is established, relationships between energy and equilibrium, such as that. Okay, I gave all of my big ideas in a couple of early examples in what I did on Thursday's lecture. And if for one reason or another you haven't been able to view Thursday's lecture yet, I really encourage you to do so. And if you happen to be one of the people who's listening in on this recording after the fact, I really would encourage you to make sure you've got video lecture 14 under your belt before you do video lecture 15, which is what this one will be. I want to spend the overwhelming majority of the time today on examples. And examples that will mimic either problem solving that's in front of you now in the homework or problem solving that is to come. Okay? I'd really like for you, obviously I always like it, my ego is appropriately stroked when you take notes over everything that I say, because I think what I say in class is important, blah, 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 blah. But today it's especially important because the techniques that I'm going to put in front of you today are going to be techniques that are going to be relevant for you as you go forth and you do your problem solving in the homework and on assessments. Okay? And I'm going to take a lot of time on two examples primarily. Okay? Probably 30 minutes per example. Not because these are especially long problems, but the logic that I'm putting into the steps that I'm taking, I want to make as vividly clear as possible. So, my path is going to be to do an example first, note the patterns that appear in that example, and then come back to how I want you to approach those patterns in a second example. The first example is going to be an example where I have a large value of the equilibrium constant K, and I have a large value of the change variable X. And you'll notice when I do this, these don't have to be really, really big values at all. But they'll be big compared to the small values I'll do later. And I'll do something very specific to simplify the algebra to keep it as painless as possible as we move forward in the story. The equation that I want to talk about in this particular story is what's known, let me say equation's a general term. Let me call it the reaction that I want to talk about in this story. It's what's known as the water-gas shift reaction. It's important in production of hydrogen gas when you actually build hydrogen reaction fuel cells. And it's a reaction where hydrogen gas can be combined with carbon dioxide on one side of the equilibrium. And on the other side of the equilibrium, that water is in combination with carbon monoxide gas. I've got an equilibrium constant for this reaction. It's a fairly large equilibrium constant as equilibrium constants go. Okay? It's at 700 Kelvin. If I was going to compare free energy to the equilibrium constant, that might be relevant. Right now, the only thing that 700 Kelvin matters for is I really want water to remain gaseous. And I'm going to keep it at a very high temperature to make sure that water remains gaseous. I'm going to have a mixture of gases that initially contains 0.0150 molar concentration of H2 and 0.0150 molar concentration of CO2. What's the final concentration of all this stuff at equilibrium at 700 Kelvin? Okay? Now, this is a little bit different than the story I was telling our last time together on Thursday. Okay? When I actually talked about what we needed to deal with our last time together, I actually gave you initial values of a thing and a final value of a thing and said, use that one final value to find out all the other final values to define an equilibrium constant. This time I'm giving you the equilibrium constant. I'm giving you initial values. I'm saying find equilibrium values of everything. If I'm going to move forward with this, I need an expression for K. Well, I write down an expression for an equilibrium constant. What do I need to write? Any reaction quotient that I ever write is written as what over what? What quantities divided by what quantities? It is the activities of the products divided by the activities of the reactants. Absolutely. And the activities in this particular case are expressed as concentrations. Okay? Now, good news in this particular bit of problem solving. Okay? This is the balanced equation. What did I not need to do to build this balanced equation? What doesn't this balanced equation have that a whole lot of balanced equations tend to have? The coefficients in front of each of the reactants and products. Yeah, I didn't need to do that this time. They'd all be 1. Well, that turns out to be really nice for writing equilibrium constants as well. And most reactions that we're going to wind up dealing with have this kind of one-to-one stoichiometry that makes the writing of these. Not all. We'll have to deal with some distinctions, but most have these types of one-to-one stoichiometry that makes the writing of the product's concentrations over the reactant's concentrations. Pretty doggone straightforward. And it's that expression that is equal to 0.106 at 700 Kelvin. What we need to do in order to solve this problem is we need values, or we need expressions that represent these equilibrium values of the concentrations of H2O and CO and H2 and CO2 under these circumstances. And how'd I get my equilibrium values last time around? I had a tabulated description of what was necessary in order to build this type of expression. And it represented the stoichiometry progress of this reaction at equilibrium conditions. It was that thing I called the ice table. And I'm going to build another ice table for this reaction. Now, I've got 4 different quantities involved in the reaction this time. And so I need 4 columns in my ice table this time. 1 column for H2. And 1 column for CO2. And 1 column for H2O. And 1 column for CO. And the first letter I stands for initial. I need initial values of each of these quantities. Well, the initial values of H2 and CO2 are given to me directly. They're right there in the problem. 0.0150 molar concentration of H2, 0.0150 molar concentration of CO2. What about H2O and CO? What does the problem tell me about the initial concentration of H2O and CO? I really don't mean this as a trick question. I mean it by what does it say in black and white up there about the initial concentrations of H2O and CO? I saw the correct gesture in the back of the room, throwing up hands. Nothing. It don't say a blame thing. And it don't say a blame thing is an appropriate response. Okay? And these problems are typically written in such a way that it just tells you the initial values of what's present. And it doesn't tell you anything about that thing being present. Guess what you're working off the assumption of? It ain't there. And the initial concentration of H2O is nothing. And the initial concentration of CO is nothing. Okay? Unless expressly told otherwise. If you see the setup of a problem like this, and it gives you initial values of two things and tells you nothing about everything else, take nothing at face value. Assume it's not there. Okay? That's the initial, that's the I. The C and I stands for change. How much do these equilibrium values change, or how much do these values change as we approach equilibrium? Well, again, I've got 0.0150 molar of H2, and I've got 0.0150 molar of CO2, and I've got nothing about the other guys. What direction is this reaction going? If this reaction is going to produce anything at all, which direction does this reaction have to go? To the left or to the right? I've got stuff over here. I've got no stuff over here. I've got to produce stuff. It better go to the right. Okay? So that means I better have positive change for the products in this reaction. That positive change is expressed by a plus X. And if I'm producing H2O and CO, where does the content to produce H2O and CO necessarily come from? It better come from the H2 and CO2. So if these change values are plus X, then these change values had better be if these change values are plus X, then these change values had better be minus X. I refer to X in this case as the change variable. It represents what's changing on both sides of this chemical equilibrium. Okay? It represents the gain of the products in the reaction. It represents the loss of the reactants in the reaction. Now, question. Okay. Oh, if you can't hear me at all, A, I'm recording these always, and B, yes, please go log out and log back in. Yes, you can't hear me. Yes, always awkward to do the private messages in when I am projecting what's on the screen. So where we stand. I stands for initial, C stands for change, E stands for what are these problems I'm working out anyway? It stands for equilibrium. Okay. Here, for those of you who do not think algebra is a good time, here's where I start the bad news. Okay? Like I said, when we went through these examples on Wednesday, we had given to us up front a value for the equilibrium of one of these things in the reaction. And we could plug in a value down here and it immediately told us what x was, and we could propagate that x through the rest of the equation and find the other equilibrium values. And a lot of the homework is built like that as well, to get you used to using these isotopes. But in this particular story, we're trapped because we have no information. In fact, the problem is expressly asking us to find the final concentrations of all materials at equilibrium. So we don't have anything we can directly put into the table. We can only put in algebraic expressions to the table. 0 plus x on the product side. 0.0150 minus x on the reactant side. That's all I got. And I've got to do some algebra somehow to come out with a result. That's the bad news. For those of you who dislike the algebra, here's the worst news. These are the quantities or the expressions that I have to plug into my equilibrium formula up here. When I write down H2O times CO concentrations over H2 times CO2 concentrations, what has to go into the numerator is X times X. And what has to go into the denominator is the equilibrium expressions down here. 0.0150 minus X times quantity 0.0150 minus X. And all that's equal to 0.106. Let me keep set aside in blue what I'm solving for here. Let me keep out all the rest of it set aside the other way. Now, if this was really, really bad news, then what I'd wind up doing is foiling through what's in this denominator and setting up a quadratic and having to solve a quadratic formula to solve this problem now. And you could absolutely do this problem this way. Okay? Thankfully, we can make things a little bit easier on ourselves by recognizing that both of these initial values are exactly identical. And we can simplify this thing out by taking what's in the denominator and numerator and simplifying it down to squared, and what's in the denominator as well and simplifying it down to squared. I can rewrite this expression like so. And once I do that, here comes the really good news. Because there's a really simple thing I can do to left and right side of this equation to get rid of the squares and get rid of any necessity to do a quadratic. What do I do to left and right side? Square root. Hoorah. And by taking the square root, I get rid of the square there. I get rid of the square there. And the square root of 0.106. I can punch that in my calculator, I swear it. It's going to be 0.3256. Okay, there still is a bit of algebra necessary here, okay? We've not gotten rid of all of the algebra we need. We've got to do some algebra to get x by itself, and it's a decimal place algebra type story, okay? All the Alex stuff I'm asking you to practice, it's for this right here, okay? It's to make something like this a little bit more comfortable. It's to recognize, hey, let's multiply left and right side by 0.0150 minus x. And hey, we can actually factor this guy in like so. And 0.3256 times 0.0150 is going to get me a really, really tiny number. X equals 0.004884 minus 0.3256 times x. Everybody good with the algebra I'm doing so far? Nobody's off song of the algebra? Okay. One thing that if you actually wind up looking up the LibreText examples that I've got linked through Canvas that you might notice different than what they're doing is I'm keeping an extra significant figure around to help me out with the rounding later. Okay, that way I make sure I'm not losing information to rounding error one way or another. So I 0.0150, 0.106, my ultimate result's going to be 3 significant figures. But in all the intermediate steps, I'm keeping 4 significant figures around. Okay? Well, I can swing this term in x over to the left. It'll be 0.3256x plus, what's the coefficient right there? It's an implied 1. So 1 plus 0.3256. And x is going to be equal to 0.004884 divided by 1.3256. And that's going to be equal to 0.00368. Okay. Deep breath, we did the algebra, right? But the algebra is not the whole solution. We can't lose sight of what the algebra means. We did all of this algebra to come up with this change variable x that we used in our equilibrium expression. You still got your ice table up the page you can go ahead and refer back to that. I'm going to just go ahead and make sure I reconstruct the equilibrium line of the ice table. The reaction was H2 plus CO2 yields H2O plus CO. And this was X, and this was X. This was 0.0150 minus X, and this was 0.0150 minus X at equilibrium. Okay? Well, for H2O and CO, that's pretty doggone straightforward. .00368 molar. For H2 and CO2, it's a little bit more sophisticated than that. It's doing my 0.0150 minus my 0.00386. And the result of that is going to be 368, fine. I had it correct in the calculator, would have come out in the wash. But by all means, interrupt me when I write something down that's incorrect. Yeah, it gives me a difference in that final significant figure I come up with. The result there is 0.0113 molar. Okay? And in red, I've got my final answers that the problem was looking for. The problem wanted the final concentrations at equilibrium for all the stuff. There's the concentrations at equilibrium for all the stuff. Okay? Well, if these are the concentrations at equilibrium, I should get them coming out to 0.106 when I actually set them up in an equilibrium expression. Let me check that. .00368 squared in the numerator, excuse me. .0113 squared in the denominator. And when I put that in my calculator, it gives me 0.1058. To 3 sig figs, that is absolutely 0.106. The equilibrium calculation worked. I just took over 30 minutes on one example. And again, when you get used to examples of this sort, I expect you'll be able to solve them a little bit faster than that. But I wanted to make sure it was plain what I was doing at each step. Do you have any questions over this? And one thing that I felt as I was going through this, and this is the second time today I went through this because I went through it for the 8 a.m. folk as well, is I felt myself really getting involved in the algebra and getting so serious about the algebra that I got lost a little bit of what I was doing the algebra for. Oh, that is so easy to do with these problems. Okay, particularly those of y'all who don't enjoy the algebra, who feel the pressure when you do the algebra yourself. Okay, it's so easy to get lost in the algebra that you will forget what X stands for. How do you know what value of X goes into the chart? Katie, are you asking very precisely about the change row in the tabulation here? How you know what we need to put into the tabulation of X and X? Yes. Okay. The change row of the ICE table goes as the nature of the chemical equation itself. Okay. Everybody is X in the table because there are no coefficients in the chemical equation. There's a coefficient in the chemical equation, I'd need to put a 2 or 3 in corresponding. I'll do another example here in a bit that drives that home a little bit more. We started with 0.0150 molar concentration of H2 and 0.0150 molar concentration of CO2. And with nothing mentioned in the problem about H2O concentration or CO concentration, we presume those concentrations were zero. If there's going to be a reaction, I've got to make H2O and CO. I have to have a positive addition to the quantities of H2O and CO present. That's why these are positive X's, because they're adding to the concentrations of H2O and CO present. They have to. We started with no H2O and CO to begin with. These are on the product side. We get H2O and CO because we have combined H2 and CO2. We have H2 and CO2 present, they start going away. And because they're going away, there are negative X's in these positions. H2 and CO2 have negative X change because 1 mole of each proportionally is going away. H2O and CO are positive X because 1 mole proportionally of those are emerging into the reaction mixture. Katie, does that help you with your question? And again, I'm going to do another example. I'll make sure I drive home what's happening with that change line in that next example. Okay? Other questions along those lines? Okay. Let's talk some about the strategy we've employed here. Okay. I'll put out several steps that you need to make sure you've done each time you do an equilibrium problem. Most problems will give you a balanced chemical equation up front. If those problems do not, you better make sure the equation is balanced. Everything that follows in one way or another is dependent upon the balanced chemical equation. And if we don't have a balanced chemical equation, the entire mentality of the problem solving falls apart. We need to make sure we have our equilibrium equation right. And again, if we don't get that equilibrium expression right, then everything else falls apart. I gave a decent amount of time to how we write down these equilibrium equations for that very reason. So you need to make sure the equilibrium equation comes in correctly. Remember that ICE tables are more sophisticated representations of stoichiometry. They represent what's actually being made in the reaction, what's being taken away in the reaction. It's important when we do these problems that we build this ICE table that accurately represents what we're given in the problem up front and the stoichiometry of the reaction we're trying to solve for. There's always going to be some algebra involved. In the examples we went over on Thursday, the algebra was very, very straightforward. Okay? In this past example, it's not quite so straightforward. In the next example we do, we're actually going to build an approximation to what we saw. But you have to apply algebra well to the expressions that result from the ICE table. And the result of that algebra is going to be the value of that change variable x that you express in the ICE table. And then we'll apply the change variable x to get equilibrium values of unknowns. The equilibrium values of H2 and CO2 in our previous example were 0.0150 molar minus the value of the change variable. And I'll just go ahead and throw 6 in for those of y'all who really like to make sure your work is rigorous before you submit it. Like to make sure your work is checked out. Use the equilibrium expression again to check your work. That's as close to a one-size-fits-all problem-solving strategy as I can come up with. Okay? I've got about 30 minutes to get through a second example. I'm going to try to get through that example as efficiently as I can. But before I go forward, I'm going to ask if there are any questions over the problem-solving strategy I've put out here. And I got a couple people still writing down notes. You might be on the Zoom as well. I want to start with a new whiteboard window for what I do next. Let me just set up what I'm going to do next. Okay. Nitrogen monoxide, NO, is an acid rain gas. Okay. NO also results from the equilibrium reaction of nitrogen and oxygen. We've got nitrogen and oxygen in our atmosphere. So it's a very appropriate question to ask. How much of the nitrogen monoxide do we generate in our atmosphere normally? So that's going to be my setup for example 2. And the theme of this example is going to be eliminating algebra by approximation. I'm going to build in something in the solution of this problem that gives me an approximation that I can work with. Here's the reaction. Nitrogen gas in the atmosphere combines with oxygen gas in the atmosphere to form nitrogen monoxide. Nitric oxide to its friends. But the equilibrium for this reaction at 25 degrees Celsius is fairly small. Small to the tune of 10 to the minus 31. We all know how big a number 10 to the minus 31 is. Yes, it's puny. Okay. And the fact that that's so small is going to be built into our thinking as we move forward. Let me whittle this down a little bit. There we go. Now, the partial pressures of these gases do reflect a little bit about their proportion in the atmosphere. This is potentially a little bit aggressive about the pressure of N2, and there probably is a little bit more O2 running around, but we'll go ahead and work with this for now. Okay? Now, note what's given you in this case. This is a story where the activities are given you not as concentrations, but as pressures. And this is implied in the case of P right here. We won't always use case of P as our equilibrium constant. But when we use case of P, what we're telling you is we're using an equilibrium constant that's built out of pressures, not out of concentrations. So the equilibrium expression this time is given as the pressures of the products over the pressures of the reactants. The pressure of NO divided by the pressure of N2 times the pressure of O2. Oh, I forgot something. Something small and subtle, but something very, very important. Is this balanced? What do I need to do to make this balanced? I better have a 2 right here. And the moment I put that 2 right there, what has to change in my equilibrium expression? What has to be squared? The pressure of NO. This is me making that point completely by accident, by the way. I just scribbled down the reaction, never paid attention to the fact it wasn't balanced. But if I have a chance to make a point, I'll take my chance to make the point. If you don't have a balanced chemical reaction at the start, everything else in that problem solving falls apart. If we have this equilibrium expression built wrong, everything else we're going to do is going to be built off of that equilibrium expression. It's this expression that's equal to 2.0 times 10 to the minus 31 at 25 degrees Celsius. Okay? Okay, let me start building my ice table. You should recognize the theme by now. Note that this time we're building the ice table, not for concentrations, but for pressures. Pressure of N2, pressure of O2, pressure of NO. First row is initial. Second row is change. I never give myself enough room to write these things out initially. Third row is equilibrium. What are my initials for the problem? What's given to me up front? This is the point where we interpret what's in the problem to actually get the correct setup. What's my initial pressure for N2? 0.78 atmospheres. And my initial pressure for O2 is and my initial pressure for NO is. What's told to me about the pressure of NO initially in this problem? Nothing. Number one. Number two, NO is an acid rain gas. And if we had substantial quantities of NO in the atmosphere occurring initially, that would be very, very bad times. One thing we better keep an eye on when we solve this problem now is we have substantial quantities of NO finally at the end of this story. That's going to be very, very bad times. Okay? Now, the change is based on the chemical equation. Okay? What am I making in this equilibrium process? I start with quantities of N2 and O2. I'm making NO. So the positive change in this story had better be the change on NO. But this time, for every one part of N2 and O2 I'm reacting, I'm generating how many parts of NO? 2. So I need that reflected in the change line of my ice table. Pressure of NO is plus 2x compared to the minus x's that results from the removal of N2 and O2 from the reactant. The coefficients, again, come from the coefficients in the chemical equation. Once again, if we don't get those coefficients in the initial chemical equation right, we don't have a balanced chemical equation, everything else is falling apart. Okay? So that's where my expressions at equilibrium are coming from. 0.78 minus x for N2. 0.21 minus x for O2. 2x for NO. Excuse me. Everybody good on how I've constructed my ice table? Any questions over this thus far, particularly about the change line, if you've got it? The most important thing I can impress on you about that change line is the place these coefficients are coming from is from the chemical equation. And there's a minus on the stuff that's going away on the reactant side and a plus in what's coming in on the product side. Okay? Let's set up our equilibrium expression. P squared of NO over P of N2 for P of O2 is going to be equal to quantity 2x squared in the numerator taking place of P and O. Quantity 0.78 minus x over quantity 0.21 minus x in the denominator from N2 and O2 respectively. Now this feels like really bad news because this time these guys aren't the same. If I FOIL these guys, I'm into quadratic land again. And I don't want to go see quadratic land if I can help it. The good news is the value of the equilibrium constant. And numbers this small might not seem like good news to you. But what's going to be tiny here? Is the numerator going to be tiny, or is the denominator going to be tiny? Numerator is going to be really, really tiny. Okay? That means x is going to be pretty tiny. And 0.78 minus a tiny number probably isn't going to change that 0.78 all that much. And 0.21 minus a tiny number probably isn't going to change that 0.21 all that much. So rather than working with algebra to save us, we're going to make an approximation this time. And that approximation is known as the small x approximation. We can eliminate the x's from the denominator if x is sufficiently small that it won't change the initial values of the reactant activity substantially. In other words, what I'm telling you in this small x approximation is that 0.78 minus x is going to be very, very, very near to 0.78. And 0.21 minus x is going to be very, very near to 0.21. And that's going to be how I get out of quadratic jail in the denominator. I'm going to use the denominator as a means to simplify and eliminate the terms that would necessitate using the quadratic formula. You can totally use the quadratic formula on this if you want. Get the same result. But if we can help it, we don't want to. So let's not. So K sub P is approximately equal to 2x quantity squared over 0.78 over 0.21. And that's approximately equal to, wavy equal sign, I swear it. And we hope on the other side that this is going to get us a sufficiently small. Spoiler alert, it totally will. For now, I'm going to say that you can use the small x approximation when the equilibrium constant is less than 1 times 10 to the minus 6. 2 times 10 to the minus 31 is a whole lot smaller than 1 times 10 to the minus 6. This is going to work, y'all. Okay? So let's show that it works. Two x quantity squared, excuse me. How do I simplify that down? Square both guys inside. It'll get me 4x squared. Multiply left and right by 0.78. Okay. Well, once I've got that in place, why don't I just divide both sides by the 4 and just go ahead and get that done. Fair enough? So x squared is equal to 0.78 times 0.21 times 2.0 times 10 to the minus 31 divided by 4. X squared is equal to 8.19 times 10 to the minus 33. Take the square root of both sides, and that'll get me an x out of 9.05 times 10 to the minus 17. We said all along that x was going to be a really tiny change variable. X is a really tiny change variable. I think it's very safe to say that 0.78 minus 9.05 times 10 to the minus 17 is going to be pretty close to 0.78. You may confirm that in your calculator if you'd like. But let me go back to my equilibrium. Okay. Once more with feeling. Pressure of N2, pressure of O2, pressure of NO. The equilibrium values were 0.78 minus x, and 0.21 minus x, and 2x. Again, because of the small x, we presume that the initial value of N2 remains incredibly close to the final value. And to 2 sig figs, that's absolutely 0.78 atmospheres. O2 is the exact same story, 0.21 atmospheres. But pressure of NO was 2x. We have to remember that x doesn't represent necessarily the final value of the thing coming to equilibrium, but it's the changed variable, and we have to multiply, in this case, that changed variable by 2 because of what's in the chemical equation. So 2 times 9.05 E minus 17 is 1.84. 1 times 10 to the minus 16. We make a tiny amount of NO in the atmosphere just through normal reactivity. But that tiny amount is so piddly small as to be, for all practical purposes, irrelevant. And it's irrelevant because the equilibrium constant is so small. Questions about that? Any questions about the problem-solving technique there? What you need to know is that the first example that I did, where I took the square root of both algebraic expressions in the algebra, very closely reflects the final problem in the section 13.3/13.4 homework set. You will use an algebraic technique very similar to that in the first example in that homework. I've not given you a homework problem yet that uses the techniques in example 2. However, the techniques in example 2, especially that small x approximation, I'm going to go over again. And it's going to be very important in where we go next. Okay? Now, I have a couple of minutes. Will you bear with me while I show you one other example of an equilibrium? And the payoff of this is I get one additional 5 minutes to show you that example that's the most important equilibrium you're going to encounter in this course. And we're going to come back to this particular equilibrium time and time again. Now, there are 2 different ways I can put this particular equilibrium in front of you. One is a way that many of you probably have seen one point or another before. That equilibrium is H2O as a liquid decomposing or dissociating into H plus in aqueous solution and OH minus in aqueous solution. Okay? For organic chemistry reasons, I actually prefer a different variety of this particular equilibrium. But whichever way I prefer it, on the left side, I have H2O in its common form. And on the right side, I have ions. One side of this equation represents a dispersed phase. The other side represents a condensed phase. Which side represents the dispersed phase? Which side's got the aqueous stuff? Right side. Okay? And which side has the condensed phase stuff? H2O is a liquid on the left. When I write an equilibrium expression for a reaction like this, I write the expression only counting the dispersed phase stuff or the condensed phase stuff. Well, what can I measure concentrations of? The ions that are aqueous. So the equilibrium expression for this system goes as H3O plus concentration times OH minus concentration. And I told you this is the most important equilibrium you're going to come across in Chem 102. It's a very consistent equilibrium. It's an equilibrium that's so consistent we consider it a constant and we give it a value that's special. We call it K sub W for water equilibrium. And the value of this equilibrium constant at 25 degrees Celsius just so happens to be 1.00 times 10 to the minus 14. Now, the reason why this is the most important equilibrium in Chem 102 is very closely aligned with that number 14. And if you've done any chemistry at all, at any point in your background, you've come across that number 14 when dealing with water or different solutions of water. Where do you think that number 14 connects with stuff you've studied before? It's close to time. I'm going to let you off the hook. What's the range of the pH scale? 0 to 14. And that's where the 14 comes from. So this is the most important equilibrium in Chem 102 because it has a great deal to do with how we measure pH in water. And it opens up to us the principles that are going to be involved in the study of acids and bases. And that's our transition coming out of equilibrium in general in chapter 13, taking us into acid and base chemistry in chapter 14. And that's got us against time. I'll see y'all on Thursday or in lab this afternoon if appropriate.